Hi everyone, this is part 2 of my video on recycling mixed metal oxide MLCCs. Today I'll extract all the metals that were left in the solution. This forbidden juice here contains a number of metal cations that were present in the ceramic from those MLCCs I dissolved to extract their internal electrodes. The setup I have here is a cheap DC power supply, graphite anode, and a copper cathode. For cathode, I'll be using those small loops of wire that I'll weigh before and after I deposit the metals on them. I'll try to selectively deposit the metals by changing the voltage. So I'll first deposit any silver and palladium that's present in the solution, then move to bismuth, antimony, tin, nickel, cobalt, zinc, and if present, and if I can actually reduce it, manganese. The starting voltage was 1.2 volts, which should reduce palladium and silver present in solution. Because there was no current draw, I slowly began to increase the voltage with hopes that it would overcome the internal resistance of the setup. Because there is always a difference between theoretical voltage required to reduce something and actual practical voltage on your system. Even after increasing it to 1.4, there was no reaction besides the remaining acid in the solution dissolving the copper. As predicted, there was no silver and palladium in solution. Same story with bismuth. The voltage only picked up when I got into the lower end of the antimony range. Increasing the voltage to 1.9 actually got it to draw some current. So yeah, there is things happening. This was also when chlorine production at the anode started. And after some time, I could see metal being deposited on the cathode. I let the electrolysis cell run until the current fell back to zero. Then I moved to antimony. At 2.1 volts, gas generation became more obvious. To speed up the reaction, I upped the voltage to increase the current. And it worked. After letting it run for like 5 hours, the current fell to zero, meaning all the metal that could be reduced has been reduced. I'll filter this because it obviously didn't stuck to the electrode. And then I'll run electrolysis at a higher voltage to reduce the next metal on the list. Here you can see what the chlorine did with exposed copper on the anode. I then moved the electrodes to another beaker and carefully decanted the solution to separate the antimony powder. At this point, the smell of chlorine was quite obvious, even after the cell was turned off for an entire night. Next metal on the list was tin. To reduce it, I had to up the voltage over 2.4 volts, but could not go much higher because I would start to deposit nickel and cobalt.
I'll shake the electrodes a bit to see if I have a connection problem. No current at 2.4. We'll have to increase the voltage. See if I can get it. Let's slowly increase the voltage. Ah, I'll do a bit more. Reaction started. It's drawing a small amount of current. Let's go up a bit.
I managed to recover a small amount of tin. There wasn't much of it to start with, so that was good. As you can see by the bubbling on the cathode, I was also splitting water to oxygen and hydrogen. This is not good because it is lowering the efficiency of the electrolysis.
Another day later, all I got was a very small amount of black powder. When compared to antimony bismuth, I am fairly certain I only reduced tin, because if I also did cobalt and nickel, there would be at least this much material.
When I moved to nickel and cobalt, the current increased massively.
There's a lot of deposited metal on the cathode. After depositing all of the cobalt and nickel,
I transferred the solution into an empty ice cream tub.
and moved the whole setup outside. I did so because, unlike previous metals, zinc is the main ingredient in the ceramic. There will be a lot more chlorine generation, and as such I cannot run the electrolysis inside even with good ventilation. This is the reason why I'm talking over the turned off setup, because I'll put on a gas mask before I start the electrolysis.
I started at 3 volts, but the reaction didn't really pick up until I increased the voltage to 4 and then 5 volts. Increasing the voltage led to dendritic growths on the cathode. It was good to see large amounts of metal deposited, But those growths may pose a problem because they can short the distance to the anode and cause my power supply to turn off. If I didn't have the overcurrent protection mode option, this would be much more dangerous and could break the entire thing. This also produced very large amounts of chlorine that would cause problems if I didn't have proper protection. This is how dendrites looked after I let them grow for a night. When the reduction was finished, I cleaned the cathode, removed the anode. Graphite was actually corroded a bit. I didn't expect that, but I heard it can happen. Then I filtered off the remaining solution that was at this point absolutely saturated with chlorine, so I saved it for some future projects and recovered the reduced metal at the bottom of the tub.
Here is a zinc powder mixed with carbon from the electrode. I'll wash it, distilled water a bit more, and melt it down. I haven't immediately washed and dried the tin powder, so all of it oxidized to tin oxide. There also wasn't a large amount of it, so I won't be weighing it. But yeah, I did get some out. Antimony powder that I suspect is mixed with a bit of tin. Likewise oxidized a bit, but there is actually enough of it, so I will weigh it. This is oxidized mix of cobalt and nickel powder. You can actually see the green of nickel and very, very dark bluish black of cobalt with a random bit of red. I'm not really sure what it is. Could be a bit of iron from this plate because I could never get all of the iron oxide from it because I use it for some previous project. I do not know the exact ratio of nickel to cobalt, but because nickel is only used as a tin plating on the termination caps, while cobalt is a part of the ceramic, I believe this is mostly cobalt. I recovered 35 milligrams of antimony powder. I also recovered a gram of nickel and cobalt. Well, a little less than a gram. There's also some oxygen and chlorine.
I really should have washed it better and dried it immediately. After weighing them, I sealed both powders in their own ampules. The time has come to melt the zinc. Well, I could absolutely use a gas torch. I believe a heat gun is a better choice. Reason for this is that zinc vaporizes and burns at a quite low temperature for a metal, and I don't want to get a zinc fume fever. Looking back, this is about the worst thing I could have done. Blowing hot air over fine zinc powder turned all of it to oxides. Once I realized this, it was already too late. There was absolutely nothing I could melt even with a map gas torch. Here you can see some small amount of zinc burning in the flame, the nice green color, but that's all about all the results I got. Weighing the oxides, I estimated I had about 20 grams of zinc. This is close to a one-third of the theoretical mass of zinc in those MLCCs I would have got if I ran electrolysis to the end. I didn't do that because it was producing crazy amounts of chlorine. If I'll ever attempt to recycle ceramic again, I'll use sulfuric acid or a base, basically anything that does not make a chemical warfare agent as a side product. Thank you for watching, like, subscribe, and see you next week.